Hello everyone, welcome on our YouTube channel Physics Made Easy Kota. My name is Daljit Kaur and on behalf of our channel, in this video lecture, I am going to explain about the chapter Moving Charges and Magnetism. This is the first part of this chapter. After this part, we again have two more parts in which we again understand some other basic concepts of this chapter. So first of all, for the first part we are going to learn about the concept of the magnetic field. Along with this, I am going to explain about the Biosavart's law, and the last one in this video is the Ampere's law and its basic application. So we are going to study all these three topics briefly. Electric field and magnetic field are regarded as a single unit, and this unit is known as the electromagnetism in physics. Actually, the electromagnetism is one of the branch of the physics. To explain the electromagnetism, there was a scientist whose name was oersted. He performed a very simple experiment to demonstrate the magnetic effect of electric current. For his experiment, he took a wire, attached it to the battery and passes the current through it. And along with this, he placed a magnetic needle close to the wire. When the current passes through the wire, he observed that magnetic needle shows deflection. So he observed that whenever a current passes through a wire, magnetic needle shows deflection, which means that electric current in a conductor produces magnetic field in the space around the conductor. So in other words, we can say that the flow of electric charges is a source of magnetic field. From his result, other scientists come into this field and they do some basic experiments, and they also prove that the law of electricity and the law of magnetisms are unified. And to explain the direction in which the magnetic field is producing, there is a rule, which rule is known as the Ampere swimming rule. This rule helps oersted to define the direction of the magnetic needle due to the electric current in a conductor placed near the magnetic needle. And from this we come to know about the magnetic field. So what is magnetic field? Magnetic field in actual a space or a region around a current carrying conductor within which its influence can be felt, and that is regarded as the magnetic field. And the strength, which means maximum or the minimum, is the magnetic field maximum or is the magnetic field minimum, that strength is known as the magnetic flux density. And there are the various units that describe in the SI system or in the CGS system for the magnetic field. For the SI system, the unit is Tesla, and for the CGS system, the unit is Gauss. And the Gauss can also convert into the SI system, as 1 Gauss is equal to 10 raised to power minus 4 Tesla. Tesla is also represented as the Weber per meter square in the SI system of the unit. So the Gauss is also related to the Tesla. So remember this formula. This formula can be used in numericals. There are the various laws or the various rules that help us to find the direction of the magnetic field when a magnetic field passes to the current carrying conductor. And for this, the first rule is a Maxwell corkscrew rule. Its another name is the right-handed screw rule. For this, we have to imagine that if a right-handed corkscrew is imagined to be rotated in such a direction that the tip of the screw points in the direction of the current, then the direction of the rotation of the thumb give the direction of the magnetic line of force. To remember the direction, there are some conventional signs used for the magnetic field. First of all, when the magnetic field coming out of a paper, or we can call it is normal to the paper, then it is represented by dot. And if the magnetic field is perpendicular to the plane in the downward direction, then it is represented by the given symbol, and also sometimes it is represented by the cross taken in a circle. So this is the first rule. Another rule is the ampere swimming rule. This rule is used to find the direction of the deflection of the magnetic needle due to electric current in a conductor. So this rule says that, like, this is for the imagination. Like if we imagine a man is swimming along the wire in the direction of the current, his face turned towards the needle so that the current enter through his feet, then north pole of the magnetic needle will be deflected towards his left hand. So both these rules are helpful to understand about the direction of the magnetic field. So now we must remember what is a magnetic field. Magnetic field is actually the space around a current carrying conductor in which its influence can be felt. And for this there are the various experiments conducted. Like for this we take a one cardboard and insert a wire inside it, then pass a current, and with the help of the magnetic needle we can find the direction and the representation of the magnetic field around that current carrying conductor. And for the easiest method to find the direction in the two-dimensional, we use the two rules that I already discussed. So this is one of the most important concept to find the direction of the magnetic field whenever a current is passing and the magnetic field is always around it. Biot law. Biot law is used to determine the strength of the magnetic field at any point due to current carrying conductor. For this, we consider a current carrying conductor and further consider a very small element AB that having the length dl and the current I is flowing through it. We have to calculate the strength of the magnetic field at a point P, that what is the strength of magnetic field due to this current element at a point P. And this point P is at a distance small r from the element, and it is found that the strength of the magnetic field depend upon the few factors. First of all, dB depends upon the dl, that is the length of the small current element. dB directly proportional to current I. dB directly proportional to 1 upon r square. R square is the distance of the point P from the current element. It also depend upon the angle theta. This angle theta is the angle between the dl and the r vector. So the dB directly proportional to sine theta. By combining all these terms, we get dB directly proportional to I dl sine theta divided by r square. And on solving the proportionality, we have the constant, that is the mu naught upon 4 pi. So the expression is dB is equal to mu naught upon 4 pi I dl sine theta divided by r square. Here mu naught is called as the absolute permeability of a free space. Permeability means capacity of a substance to have magnetization in the presence of the magnetic field. So after solving this, we have a particular relation for the dB, and there is some standard value allotted for the constant mu naught upon 4 pi. Mu naught upon 4 pi is equal to 10 raised to power minus 7 Tesla meter per ampere. We already discussed about the units of the magnetic field in a SI and as well as in the CGS system. Our next topic is the magnetic field due to straight current carrying conductor. For this, consider the observation point P, that is at some distance from the center, and at that point there are the two angles phi 1 and phi 2, and we consider the infinitely long conductor, and this observation point is a P and it is a distance R, and the current I is flowing through this infinitely long conductor, and the expression for the magnetic field due to straight current carrying conductor is given as shown in the video. So this is expression whenever the current is flowing in a straight current carrying conductor. Earlier expressions show of any type of the conductor. And if we consider that the observation point is near one end of a conductor, then the expression for the infinitely long conductor get changed and we have the new answer for the magnetic field. And now we are going to understand what are the magnetic field lines. So first of all, consider a bar magnet. Bar magnet have the two poles, south pole and a north pole. And we can perform a very simple experiment like sparkling of the iron fillings, and to place a magnetic needle at a different points around the bar magnet, we come to know that there is some area in which the influence of the magnetic field can be experienced, and that area is known as the magnetic field lines. Magnetic field lines are closed continuous curve, they never intersect, and when if we draw a tangent at any point on the magnetic field line, it gives the direction of the magnetic field at that particular point. They are used to represent the magnetic field in the region. So with the help of the magnetic field lines, we generally represent the magnetic field. These are not in actual, these are imaginary, but they give us the idea of the space or the region in which the influence of the magnetic field can be experienced. Outside a magnet, the magnetic field lines are directed from north to south pole, and inside the magnet they are directed from south to north pole. The magnetic field lines are represented in a different way for the straight current carrying conductor. So for the straight current carrying conductor as shown in the given figure, and the current I is flowing through it, the magnetic field lines are the concentric circles, and these concentric circles have a center at conductor and in a plane perpendicular to the conductor, and we can easily find the direction of the magnetic field in this case also. But for the straight current carrying conductor, we apply some different rules. This rule is different from the rules that we discussed earlier, and this rule is applicable for the straight current carrying conductor, and this rule is known as the right hand thumb rule. Right hand thumb rule is useful to find the direction if we are aware about the direction of the current. So if we already know the direction of the current, then we can come up with the answer what will be the direction of the magnetic field lines in a straight current carrying conductor. Imagine we have the current carrying conductor in our right hand. Hold it properly in the grip of the right hand in such a way that our thumb point in one direction, and that direction is taken as a direction of the current, and then there is a curling of the fingers, and that curl represent the direction of the magnetic field lines. So in this way we can able to find the direction of the magnetic field line by the simple use of the right hand thumb rule. Remember to use your right hand, not your left hand, to find the direction of the magnetic field. Our next topic for today's video is magnetic field on the axis of the current carrying circular coil. Of course, the circular coil, you all aware this is a circular loop, and we have to calculate the magnetic field at a particular point P as shown in the figure. So imagine a current is flowing through this circular coil, and the current is flowing in the anti-clockwise direction, and the circular coil has a radius small r, and we consider the a loop is made up of a very small current element through which the current I is flowing. And to calculate the magnetic field, first of all we consider a small current element, and after this at a point P, which is away from the distance x from the center O, at this point we have to find the magnetic field, and the angle between the dl, that is the current element length, and the distance of a point P from the center is 90 degree, because the point P is in a perpendicular direction to the axis of the loop. So we can apply the Biot law. After the application of the Biot law, we come to the answer that B is equal to mu naught n I r square divided by 2 r square plus x square raised to power 3 by 2. So here r, as clearly shown in the diagram, this is again radius of the coil and represent the number of the turns. Like if we increase the number of the turns of the coil, then it get multiplied for the answer of the magnetic field. I is the current. We can also do some special cases for the case, like if we consider the point P is at the center of the coil. If we take the point P at the center O, then of course x is taken as 0. Then after calculation we get an answer B is equal to mu naught n I divided by 2r. Then there are certain rules in which we can able to find the direction of the magnetic field that we will discuss in our next video. Hope you can understand it properly. Try to remember the answers.